Hey guys, so as promised, here are the lecture notes for 2-7, what we did in class today. Sorry the internet was so terrible. Hopefully they'll get it fixed and we will not have to do this every time for both of our sakes, but just we'll run through these notes for you. So what this section is about is it kind of gives us some general theorems about polynomial equations and then how to use them and kind of how to apply them. So this is the first theorem. The theorems, they're theorem 1, theorem 2, just the order they have them in the book. That's not any kind of importance, but this first one does have a special name. It's called the fundamental theorem of algebra. And so what this one says is, in the complex number system consisting of all real and imaginary numbers, if p of x is a polynomial of degree n, complex coefficients, then the equation p of x equals 0 has exactly n roots. And you may have already kind of noticed this pattern. Basically what it means is if we have a cubic, this or something, okay, it's going to have 3 roots. So whatever that degree is of that highest degree term, the polynomial is going to have that many roots. And a little disclaimer here is that we are going to have to count double roots as 2 roots, triple roots as 3 roots, etc. So as long as we make sure to include those as 2 or 3, or if we have even more, all right, we'll be all set. But in general, whatever the degree is of the polynomial, it's going to have that many roots. That's all the fundamental theorem of algebra is stating. Next up, we have what's called the complex conjugates theorem. All right, and this is something you may have already noticed as well. If p of x is a polynomial with real coefficients, and a plus bi is an imaginary root of the equation, p of x equals 0, then a minus bi is also a root. This is just a consequence of the quadratic formula, how you have that plus or minus the discriminant term. So if you have one form of that imaginary number, a plus bi, its conjugate's also a root. So for example, if 2 plus 3i is a root of some polynomial, that means that 2 minus 3i is also a root every single time. This third theorem, very similar to the second theorem about the complex conjugate theorem. It's basically just extending it to radicals. And once again, it's a consequence of the quadratic formula, how it's that plus or minus the discriminant. So this third theorem says, suppose p of x is a polynomial with rational coefficients, and a and b are rational numbers, root b is a rational. If a plus root b is a root, then a minus root b is a root. So just like before, if we know that, for example, 2 minus root 5 is a root, then 2 minus root 5 is also a root. Pretty straightforward there, but both of those, second and third theorem, are going to be quite useful because a lot of times you're given one root, you're immediately given the other just due to these two facts here. Theorem 4. If p of x is a polynomial with odd degree with real coefficients, then the equation p of x equals 0 has at least one real root. So we kind of talked about this in general before, maybe not just formalized it in a theorem. Basically, if we have an odd degree polynomial like a cubic or fifth degree, it's got to have at least one real root. And that is just kind of due to the fact that when you take a look at the graph, one end is always going to have to be crossing that x-axis at least once. All right, just due to the form of how these odd degree polynomials work. So like a cubic, for example, it's going to take one of these two forms. In both cases, it will have that one real root, and that is the minimum for any odd degree polynomial. Not the case for even. We've seen quadratics, quartics with no real roots. That can happen. But if it is odd, it's got to have at least one real root. And the last theorem. So this is stating for this equation, this is just the general polynomial there. It's giving us a way to find the sum of the roots and the product of the roots for any polynomial. The sum of the roots is going to equal negative a n minus 1 over a sub n. And so what that means, there's a lot of notation there, but up top here, so it's just negative 1 times the coefficient of the second highest degree term a sub n is just the coefficient of the highest degree term. Awesome. So I'll show you an example of how to work with that in a second. Let's go on to the product of the roots. The product of the roots is going to depend on if the polynomial is even or odd degree, that is. So if it is even, and if it is odd, it's just that same thing multiplied by negative 1. Awesome. And here a sub n is the same as above. A naught, that is just the constant term. And here being the degree. So a quick example of using this here. Let's say we want to know the sum and product of the roots for 2x cubed minus 5x squared minus 3x plus 9. So I'm just going to use that theorem right up there. So let's get the sum first. So the sum is just going to be negative 1 times our second highest degree term, which in this case is negative 5. And then divided by our leading coefficient, so that 2. So that will just be 5/2. The product. So since we have a cubic here, n is odd, so we're going to use this one here. So it's negative 1 times our constant term, which is negative 9, over our leading coefficient, which is 2. You know, I'm a mind reader, so I maybe even just hearing you guys, you watch this video, who cares? Why would I ever want to know the sum or the product of the roots? Doesn't seem necessary at all. Well, it's actually going to be quite useful to kind of, if you're given a root, to build an equation of that polynomial. These rules will help us, as some of the kind of next examples I do will show you. So hopefully that is reason enough for you to think that this theorem is useful. Okay, and it's actually going to give us a great way to kind of build quadratics, build equation of quadratics when we have their roots. So thinking about this in terms of the general quadratic, ax squared plus bx plus c equals 0. And so if I wanted to get the sum of the roots and the product of the roots for the general quadratic, well, we know the sum is negative 1 times that second term, which is b here, so negative b over a. The product, because this is an even degree polynomial, is going to be our constant term, which is c, over our leading coefficient, which is a. All right. So I'm going to kind of rewrite this general quadratic, the ax squared plus bx plus c. The first thing I'm going to do is I'm going to divide the whole thing by a. So it would look like this. So we'll just have x squared plus b over a x plus c over a equals 0 still. 0 divided by a is still 0. And we kind of noticed that we got something close here. We got the c over a here, and we got something approaching that b over a there. I'm just going to do kind of one last more little trick here, because I have plus b over a here and minus b over a here. So I'm going to rewrite this as x squared minus negative b over a. Subtracting a negative, same thing as addition. And there we have it. So basically, anytime you have a quadratic, it is in the following form. It is x squared minus the sum of the roots times x plus the product of the roots. So that's going to give us a big time boost and just a very quick way to kind of build the equation of a quadratic just using the sum and product of the roots. All right, so every kind of general quadratic can be written in this way. So let me just show you an example kind of using this rule here on this next slide. So find a quadratic equation with 2 plus 3i as a root. I'll write our rule that we were just working with on our previous slide up here. X squared minus the sum All right, so the first thing we're going to do is we're going to use the complex conjugates theorem, because first, we know this is a quadratic, but we're only given one root. Luckily, if we know if 2 plus 3i is a root, we immediately know that 2 minus 3i is also a root. So great. So let's just that's all of our roots because it's only degree 2. So let's just get the sum and the product here. So 2 plus 3i plus 2 minus 3i. The 3i's will just cancel out, and we'll be just left with 4. And let's do the same thing for the product. So 2 times 2 is 4. The middle terms will cancel out. We'll have 3i times minus 3i, which is minus 9i squared. So this will be 13. And now we just kind of fill in the gaps here. X squared minus our sum, which is 4. X plus our product, which is 13, plus 13 equals 0. So that is the equation of a quadratic with 2 plus 3i as a root. Did it nice and quickly using that theorem involving sums and products of roots of polynomials. Now it is possible to do this another way, using kind of just writing each root as a factor. So writing them like this. Sorry, I made a mistake here. It should be minus. So you'd write each of those roots kind of in the factor format and just multiply them out. But to me, I don't know if I really want to be doing that kind of multiplication. Seems a little bit more difficult than this method up here. But if done correctly, that should work, and you should end up with that same answer up there. All right, so last example I'm going to do on this video. Find a cubic equation with integral coefficients that has no quadratic term, and 3 plus I root 2 is one of the roots. All right, So kind of some key info here. We got a cubic, so not a quadratic, so we can't kind of use the same thing we did last time. No quadratic term, that's going to be important. And it is 3 plus I root 2 as a root. And by the complex conjugates theorem, we know that 3 minus I root 2 is also a root. So great. And let's kind of also think about, this is going to be in some form with no quadratic term. It's going to be like ax cubed. There's no bx because there's no quadratic, so just plus cx plus d equals 0. So that's the format it's in. If I was going to find the sum of the roots here, so it's odd, so we know it's going to be our constant term divided by our leading coefficient. My bad, I wrote the equation of the product of the roots here. It's my bad. So sum of the roots, of course, is negative a n minus 1 over a sub n. All right, so perfect. So here we notice we actually don't have this term at all here. All right, with no quadratic term. So that value is going to be 0 over our leading coefficient a, which means the sum of the roots is going to be 0. So that's going to be kind of quite valuable information here. If we know 2 of the roots, let's name our third root r. We can kind of figure out, so the sum is just going to be 3 plus I root 2 plus 3 minus I root 2 plus r equals 0. All right, let's just solve this for r, and then we'll have our last root. So these will cancel out. 3 plus 3 is 6. So r will equal negative 6. So that's our final root. All right, so we still need to build our cubic, but at least we have our 3 roots. So what I'm going to do next is to build the cubic, I'm going to make a quadratic with these 2 terms. We saw how easy that was in the last example. And then once I kind of have that quadratic, I can multiply through by the x plus 6 for that last root of negative 6, and then I'll have my resulting cubic. So let's make a quadratic again. We know that a quadratic with those 2 will have that same form, that x squared minus the sum plus the product. So let's get the sum and the product of that quadratic. Be careful not to just recycle the sum from that cubic, because we're trying to make this quadratic here first. So this is going to be 3 plus I root 2 plus 3 minus I root 2, which will equal 6. The product is going to be 3 plus I root 2 times 3 minus I root 2, which will be 9 minus I squared times 2, which is 11. All right, great. So that quadratic is going to be x squared minus 6x plus 11. And so all we got to do to figure out the cubic is just use this last root, negative 6, and just multiply through. So we'll just have x plus 6 times x squared minus 6x plus 11. Let's just FOIL this through here. We'll have x cubed minus 6x squared plus 11x plus 6x squared minus 36x plus 66. So just to finish this off, we are almost there. 6x squareds cancel out, which they should, because remember, we don't want any quadratic term. That was one of the characteristics at the top. So x cubed, 11x minus 36x will be minus 25x plus 66 equals 0. And there's our answer right there. Once again, you could have done this by just multiplying out the three factors here, x minus 3 plus I root 2, x minus 3 minus I root 2, and then x plus 6. Multiply that all out. If done correctly, you would have gotten this same answer, but I think this method is much, 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 much easier. All right, so that's it. That's what you guys missed in class today. It's probably better. You got it. You got the no mask version, but hope this helped, and see you guys soon. Hopefully with better Wi-Fi next time.